Okay, let's talk a little bit about analog. Um, what is analog? Well, it's a little bit different than what we talked about previously. In the previous videos, we basically talked about discrete digital inputs and outputs, right? You notice that my push buttons gave a digital input of 0 when it wasn't engaged and 24 when it was engaged, right? Or my photo sensors, when something's in front of it, it gives 24 volts. When things are removed from in front of it, it gives 0 volts. So, we've been talking a lot about discrete digital inputs and outputs, basically 0 or 24 volts. The 24 volts would operate things like the ice cube relays or the motor starter, which would do these lights and stuff like that. But now we're going to talk about something a little bit different, where you don't just get 0 or 24. In fact, you will get a signal upon, on a range. And that's called analog. And there's two different types of analog. There's a current type and a voltage type. We are actually going to be talking about the voltage type because this PLC only takes the voltage type. In this case, it's 0 to 10 volts. And so what is a 0 to 10 volt analog input channel? Well, it accepts anywhere from 0 to 10 volts, right? And so you will have certain input devices like a temperature sensor or a pressure sensor, that there's always temperature, so it's always going to give some value, but a resistor inside of it just changes to where your voltage that's presented to the input terminal on the PLC changes, and that's basically your analog channel. And the difference in voltage that's presented to your input terminal basically tells the PLC what value. You basically scale it to figure out what temperature you're at or whatever, but that's pretty much it. It just communicates a certain value upon a continuum, so that you can have multiple values with the same input. Basically, like weight, you have a lot of different values, or pressure, or you just kind of have a lot of different values with analog. So that's pretty much the idea. So let's get into some examples of it, and it may get a little bit more clear as I go. Let me turn my meter on, and you might have to zoom in and zoom out. But let's zoom in. Now I've got my two analog inputs on my two channels. These are my two analog channels, this function block diagram you've seen before. But basically I've just got my two analog inputs, and I've just put little gain blocks to kind of show you what they do and how, the basics of scaling. We're not going to get into anything terribly complex, but I do want you to get the basics of what they are and scaling. Okay, notice here, this block, gain block, you have 255 and 10 over here. Okay, now this 255, you'll notice these values will change as I turn this dial on this potentiometer. Turning the dial, and you see how those values are changing? It's kind of taking my computer a little time to catch up, but you see how the values are changing? I'll show you how that works. And you'll notice the highest value is 255 and 10. This is a 10 volt analog channel, and 255. Now that number is basically an analog value number. This is an 8-bit analog channel, which means basically if you take 2 and you take 8 2s and you multiply them together. So do this on the calculator with me, and you'll get 256. You'll get 2 times 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 2. If you multiplied 8 2s, you got 256. Well, that's 255. It's basically an 8-bit channel. Now, just to warn you, this is a very low resolution analog channel with this PLC. Most that you will encounter in the real world are much higher. You'll get 16 or 32 bits, which have over 2,000 in that value. And basically what that value allows you to do is, if you have the same range, but you have more numbers within that range, it's called resolution. It's higher resolution. It basically allows you to pinpoint a value much more precisely. It's all about precision. This doesn't have high resolution, so the precision isn't great, but it's good enough for me to show you the basics. But you will see more precision with the higher resolution. With the 16-bit channels, for instance, are over 2,000, so you'd have 10 times the resolution, basically. So hopefully that makes sense to you, but let's just look at it with the voltage meter. I'm going to put my meter, my potentiometer here is on analog channel D. So I'm just putting my meter terminals on there. You probably can't see my meter terminals, but you can see my meter and you can see the screen, and that's really what I want you to focus on, the meter and the screen. Actually, my signal that I'm sending is 11.73. It's a little bit high, so you notice this channel only goes to 10. It only goes to 255. It kind of maxes out at that. But notice when I turn my potentiometer, you'll notice this value is changing. Now we're at 8.93. Now, like I said, the resolution isn't that great with this and the scaling. This says 8, this says 8.93. But basically, this is what you really want to focus on. This is the real voltage. And this number is 227. So remember, 8.93, 227. All right, yeah. Okay, and as my voltage drops to 6.78, that number dropped to 1.72. Now, you may ask, how do I come up with these numbers? Well, first of all, I know it's a 0 to 10 volt analog channel, and I know the range of my analog signal that the PLC sees is going to be 0 to 255. So the simplest way, now there is a formula that I will get into in a more, with my temperature sensor, it gets a little bit more in depth, but this is just the most simple thing I could start with. Basically, the PLC sees this number as the 255 as the highest range that the PLC sees. So basically, my rate of change, how do I explain this? If I'm seeing 255, basically, you can understand, I guess, if I go down to, let's see, if I go down to 1 volt, I'll basically have 25.5. Basically, every volt is 25.5, I guess you could say. So when I apply volts, every volt applies 25.5, and it just kind of ramps it up. Well, to get meaningful information, we have to basically scale it to volts. So the easiest way I know to do it with that is you just, basically here's our linear equation. And my rate of change with my analog value, when my analog value changes by 1, how does my volts change? Well, 10 divided by 255. You just take the voltage, highest number of the voltage, the highest number of the analog value, and that's pretty much your rate of change. I know that may not make much sense to you because I didn't explain it very well. I'll actually explain the equation a little bit better, but I just want you to get the basic idea that your highest analog value that the PLC reads is 255, and if you take 10 divided by 255, you will get the number of volts. This just only does it to the closest to the integer. So when it says 3, it's really between 3 and 4, but we could always pinpoint it. Like I say, this 89 is actually a little bit more precise than just that 3, right? What is it really? Well, our 89 is really, let's see here. Oh, I put that on the wrong stuff. Our 89 is really 3.55. So see, it's more precise if you can kind of look at it with a meter. And the 89, obviously there's more values. This is 0 to 255 versus 0 to 10. So you're going to get more precision focusing on this. But that's just kind of the idea behind analog. Like I say, this isn't the greatest analog channel with the greatest PLC, but it kind of gives you an idea of analog, right? Let's go to a temperature sensor, and I'm going to show you something a little bit more, okay? I'll actually probably get into the formal equation on this one, and hopefully I can explain that well to you. Okay, we have a temperature sensor. This basically changes... basically the resistance increases and decreases when temperature increases and decreases, right? And so the resistance causes the voltage drop, which basically causes the differences in voltage, right? So right now, see, this is actually my temperature sensor, and I wanted to change this analog value that goes from 0 to 255 to temperature. Now you're not going to see the 0 to 255 here because there's a huge range, and you don't really get, you always have a resistor in here, so you don't really get 0 to, 0 resistance, right? But anyways, you'll see kind of the same type of thing. Right now at room temperature, my analog value is 94. My temperature is 78. That makes sense. I mean, it's fairly normal temperature. It's a little warm, but whatever. But anyway, and you will notice I have a cup of ice. And so if I stick this temperature sensor in the cup of ice, let's just see what happens. You see how I went down to 93 and 92. See my temperature, it's going down. You see this is my analog value. Oh, I lost my little temperature sensor out of my ice, so it'll go back up temporarily. But you notice, if I can keep it in the ice, you'll notice these two values will be going down. This is my analog value that the PLC sees, and this is my scale value that tells you what temperature we're basically at. And I can put my meter on the analog channel, and you can see 3.57 is the actual voltage. Basically, you notice my my precision, my my resolution isn't that great, because you'll notice it flips. It only, every one of these numbers actually changes it by 12. So I can only get the degrees to, within about 12 degrees. It's terrible resolution. But anyways, you'll notice I'm down to about 30 degrees. Well, that makes sense because it's ice. 30 degrees is basically the freezing point, and we're at 356. So right now, this temperature sensor is sensing that we're at the freezing point of about 30. See how it's kind of vacillating between 42 and 30. So it's a little bit above 30, but it's trying its hardest to stay at 30. So we're closer to 30. I know that. And I know since it's ice, that makes sense. So we're 30 degrees. The voltage is 356. Let's just take it out to room temperature. And I want you to watch as this warms up, the voltage will increase and the analog value will increase and the temperature will increase. So as voltage is, you'll notice the voltage increasing. I mean, we're out in room temperature. See, we're already at 362, and we're already back up to 66 degrees, 365, So as I keep that out at room temperature, you'll notice this voltage goes up as the temperature sensor adjusts. It's just adjusting the resistance. So we're back up to 367, and our analog value is 93, and our temperature's up to 66, and eventually when this warms up, it'll get to about 78 in this room, right? Now, let's see what happens when I put on the heat to it. I have a hair dryer, and so see this voltage 369. Okay, now we're getting pretty close to 78. It's vastly okay. So 78, and my meter just moved. Okay, so 369. Our analog value is 94. Our temperature is basically 78. Let's increase our temperature a little bit and see what happens. See, my temperature's up to 90 and my voltage is 374. Temperature's up to 102 and my voltage is 3.78, 3.79, 3.8. See how my voltage on my meter is increasing as my temperature down there increases. I'm at 114, and that's good enough. You see my temperatures, so my analog value is 97, my temperature value is 114, and my voltage, if I keep it on the leads, is 3.82. So hopefully you've noticed my, basically, the temperature sensors, it senses the temperature, it sends a signal which is a little bit higher, a little bit lower voltage depending on the temperature, which can be scaled. Now, how is this scaled? Well, I'll pretty much show you. I don't want to bore you too much with the intricacies of the math, but here's basically the table I came up with. And I know this is, just, kind of chicken scratch to you, but basically what I did is when I had a thermometer, and when I got my temperature sensor down to 42, I was reading 91. And when I got my temperature sensor to, the thermometer up to 102, and my temperature sensor was with the thermometer at a temperature of 102, my value was 96. So basically, what I came up with is my slope basically is mx plus b is the y equals mx plus b right here. This is our equation for our slope. This is the slope. This is the offset. This is just kind of a linear equation. And I noticed right here with this value, if you'll notice, basically we change by 12. For every one of our analog values, every time our analog value increases by 1, this increases by 12. So slope is 12. And when you work the formula, which I'm not going to bore you with all the details, our offset was negative 1050. So how did I come up with these numbers? Well, I just plug them in there, and my slope right there is 12. You see here, y. Now, my equation that I always teach people is y equals mx plus b. There's a little bit different. This a divided by b is actually m, and this c is actually b. So basically my offset, here's my equation for this, and my 12 is my slope, and the denominator of that is just 1 since it's 12, and then there's my offset right there, which is negative 1050. So 12x minus 1050. That's just basically how I scale it. Anything that's linear, I just use the linear equation and I plug it into the values. Unless you're a math whiz or a math teacher, that may or may not make much sense. Just know that there is a scaling process so that we can apply an analog signal to a PLC. It gets a certain number that may not make sense to you, but then there's scaling to where we can turn it into a value that makes sense, whether that's we want to know the voltage that's being applied, or we want to know the temperature or the pressure or something. There is a scaling. So I may not have been the greatest teacher at that. It's kind of a complex thing to teach, even though it's actually fairly simple complex. It's just, hard to find the words to convey to everyone clearly. But hopefully you can kind of see how analog works. Now also know that analog not only is input, but there can be analog outputs. For example, with a VFD, you want to select the frequency to change the speed of the motor, and the wires sent from the PLC to the VFD, they are analog, and so the stronger or weaker the signal gets, the frequency is more or less, and it changes the speed of the motor. So like I say, you can have inputs and outputs. Inputs would be like temperature sensors, pressure sensors, even dials, like turn dials like this potentiometer, and outputs would be something like speed of a VFD. But anyways, we're going to stop this video, and then we'll get back with you on the next video, and we're going to kind of use some programs to show you how you can use these inputs to trigger outputs. Okay, so until then, we'll see you later. Thank you.